Hello, everyone. Welcome to the second lecture of the topic uniqueness problem in geometric analysis and Lojasiewicz inequality. So let me briefly tell you what's the goal of the second lecture. So we are going to prove Simon's Lojasiewicz inequality. Before we start to prove Simon's Lojasiewicz inequality, we need to set up everything, because Simon's Lojasiewicz inequality is an inequality for infinite dimensional space and for specific kinds of analytic functionals. So we need to set up everything, and this is slightly more complicated than the finite dimensional case. All right, so we start by considering that sigma is an n-dimensional submanifold. We assume that it is smooth, and this is an isometric embedding. And so in general, for an extrinsic problem, for instance, if you want to study some surface in the Euclidean space, then they are already submanifold in the in Rn. If we are considering, like for instance, a submanifold in some ambient manifold, or we just consider some variational problem on a fixed manifold, we can always use Nash's isometric embedding to isometric embed the ambient manifold to a Euclidean space. So we can always do this. Then we consider a vector bundle V. It is the union of Vx, where x are the points on the submanifold. And here, each Vx is a Q-dimensional subspace of another Euclidean space, say Rp2. And they vary smoothly with respect to the point x on the smooth submanifold. For example, if we consider that the vector bundle is the tangent bundle of the submanifold or the normal bundle of the submanifold, we can always find that the Vx is just a subspace of the ambient Euclidean space itself. So then in that case, P2 equals to P1. Of course, it could be more complicated vector bundles. And then we'll just adapt the notations that we can define the section space. And for instance, L2 is just the L2 integrable sections in this vector bundle. CK is just K times differentiable sections in the vector bundle, and the CK alpha is the holder space of the sections in the section in the vector bundle. So these are just the classical, just follow our classical definitions, but we are adapted to the sections of a bundle. And we'll consider about the derivative of the sections. So suppose U is a section, say it is a C1 section in the vector bundle. Then we can take the gradient, and the gradient is defined via there are a lot of ways to define the gradient. For instance, if V is the tangent bundle, then we have the so-called Lojasiewicz connections, which is a standard way to take derivative of sections of the tangent bundles in Riemannian geometry. And in general, the derivative, or we could say the gradient of U, takes values in the tangent space tensored with this fiber of the vector bundle. And this can be viewed, this is actually a subspace in RP1 tensored with RP2, because the tangent space lies in RP1 and the vector fiber of the vector bundle lies in RP2. And we can identify it with RP1 times P2 with the usual identification in linear algebra. Okay, and finally, we can define a function f. So f has three variables, x, z, and eta, where x are the points on the submanifold, and z belongs to RP1, which corresponding to the tangent vectors on the submanifold, and eta belongs to RP1 and P2. So later, you can imagine that the variable eta are corresponding to the gradient of the sections in the vector bundle. And we assume that f is smooth with respect to these three variables. And finally, we define a functional f, which for any u, which is let's say a C1 section in the vector bundle, fu is defined to be the integral over this manifold sigma f, where x belongs to the submanifold, and u is the section and the gradient of u, which is the derivative of this section. Okay, and you can see that they are exactly the elements in the space with the correct dimension, and we define this for C1 sections. Okay, so this is our basic setting. If you're familiar with any one version of calculus of variational problem, you probably be already familiar with this notation. And in particular, this functional will play the role as the function, as we discussed last time in finite dimensional setting. And this functional is defined over the infinite dimensional space. At this moment, it's defined for C1 sections in the vector bundle. Okay, and then next we're going to study the variational problem of this functional. So in other words, we want to understand that what would happen, what describes the infinitesimal variation of this section U. Okay, so this is our functional, and we define the so-called Euler-Lagrange operator, which we'll call it F. It sends C2 sections in the vector bundle to a C0 sections in the vector bundle, and it is defined as follows. So consider we take the derivative of the functional f at u plus sv, and we differentiate the variable s, and we evaluate it at s equal to 0. So you can see that this is the infinitesimally small perturbation near the section u, and this is defined, and we define the Euler-Lagrange operator satisfies that the infinitesimal perturbation of this functional equals to this Euler-Lagrange operator acting on acting on u, and take inner product with v in the L2 space. So here we assume that the u and the v both lies in C2 space. Okay, so you can see that in other words, this Euler-Lagrange operator can be viewed as the derivative of this functional. Of course, this is an infinite dimensional. This is an infinite dimensional analogy of the finite dimensional derivative. So in other words, this can be viewed as the Euler-Lagrange operator can be viewed as the gradient of a functional. Right. So for example, if this functional is the Dirichlet energy, so in this case, we can imagine that on our submanifold, we consider the trivial line bundle where the sections are just a function, and the variation of a function which set the variation of a function with the Dirichlet energy. We can see that if we plug it in, we know that by integration by parts, we can see that this Euler-Lagrange operator is the Laplacian operator. Okay, so another example is that if this functional is the area functional, namely, if we consider a given hypersurface and we consider that U is we consider that the U is a graph of the given hypersurface, then the Euler-Lagrange operator is exactly the mean curvature vector. Mean curvature dynamic operator. And moreover, we can see that if U is a critical point of this this functional f, then we see that for any given V, the Euler-Lagrange operator acting on U has to be 0, because for any other V, this inner product has to be 0. And for that case, we see that this function, this section U satisfies the so-called Euler-Lagrange equation, which is the reason that we call it Euler-Lagrange operator. And for any section satisfies the Euler-Lagrange operator, satisfies the Euler-Lagrange equation, it is called the critical point of this function, or we say a stationary point of that function. All right. So one important thing about the Euler-Lagrange operator is that the Euler-Lagrange operator is not linear. So it can be a non-linear operator, and we will need to study the further linearization of this operator, and we define another linearized operator called L, and L is defined to be as follows. So if U is a C2 section such that it is a stationary point of the functional, then we define the linearized operator as follows. So the linearized operator L F U is defined acting on V. So U is this stationary point, and we can talk about the linearized operator, and LFU acting on V equals to we differentiate this Euler-Lagrange operator acting on U plus SV with respect to the variable S, and evaluate at S equal to 0. So here we assume this operator is defined for our C2 sections. Okay, and this can be viewed as a linear gradient of a functional at a stationary point. Right? And this is first difference between finite dimensional problem and the infinite dimensional problem. So in the infinite dimensional case, if we take the gradient, like here we consider the Euler Lagrange operator, it may not be a linear operator. And we need to further linearize it to get a linearized operator. In the following, we'll consider a special case where this linearized operator at 0, L equal to LF0, being an elliptic operator. Okay, so we'll consider the linearized operator being an elliptic operator because later we will see that there are a lot of nice properties of elliptic operator. If you do not familiar with elliptic operator theory, you can imagine that the elliptic operator makes the infinite dimensional problem more or less looks like a finite dimensional problem. So we can use some tools, special tools that can to handle with elliptic operator, which to allow us to use some similar arguments in the finite dimensional space. Of course, for arbitrary general operator, there are a lot of theory does not. There are a lot of theory which do not work in general. Okay, so now I can state the Simons-Lojasiewicz inequality. So suppose the previous function f is smooth, and all the derivative with respect to x up to order 3 are real analytic functions of the variable z and eta. Okay, so we want to put this problem in as a we want to make the problem as a sub problem in the Euclidean space to talk about analyticity of the functions. Of course, you can also do that intrinsically, but extrinsically makes things easier. So we view the manifold, submanifold asymmetrically embedded into our Euclidean space, and we also consider that the vector bundle can be viewed as a subspace of another Euclidean space, which makes us easier to talk about analyticity. And then we see that we have an analytic functional. All right, and now excuse me. So now we are also assuming that we are considering the problem near a stationary point, which is exactly u equal to 0. Okay, we assume that the 0 section is a stationary point to our variational problem, namely the Lagrange operator acting on 0 gives us 0. Okay, so in the following, for simplicity, we'll sometimes omit the lower indices as if we, oops, sorry. So we'll omit the lower indices for simplicity. If we fix, so we'll always fix functional. Okay, so now I can state the Simons-Lojasiewicz inequality. So there exists a beta, the exponent, lies between 1/2 and 1. And there exists sigma 0 greater than 0, and there is a constant greater than 0. Of course, all these constants only depending on the functional near this 0 section, such that for any u which is a third order differentiable section of the vector bundle. Of course, here the regularity is not optimal. We stated for simplicity. And we assume that the third order, the C3 norm of this section is bounded by this small number sigma 0. Namely, we only consider a small neighborhood of the 0 section. Then we have the following inequality, where the value of the functional at u minus the value of the functional at 0. Here we assume, later we can assume, for instance, it is 0. To the power of beta is bounded by C times the L2 norm of the section, which is the we use Euler Lagrange operator acting on this section U L2 and takes this L2 norm. Okay, so this is Simons-Lojasiewicz inequality. Okay, so let me just write down the classical Lojasiewicz inequality here to compare them. So in classical Lojasiewicz inequality, if f is an analytic function and p is a critical point, then we have fx minus fp, where x is in a small neighborhood of p, to the power of beta. It is bounded by c times the gradient of f at the point x. So you can see that this is exactly the analog of value of a function. Now is the difference between the value of a functional taking value at different points, and this is exactly the analog of gradient. Right, and just recall that the Euler Lagrange operator, which is can be viewed as the derivative or gradient of the functional. It comes from taking the derivative of the functional, and so this is exactly the gradient. But here we need to specify in the L2 space. Okay, so later you will see that the infinite dimensional problem, it is very complicated because there is no single space. We need to play with different spaces. Unlike in the finite dimensional space, all the space can be viewed as some part of the Euclidean space. So here we have a lot of spaces, and actually we will use we will jump between the holder space, the Sobolev space, and sometimes we'll also discuss about the CK function space. Okay, so this is the discrete statement of Simons-Lojasiewicz inequality, and how to prove it in infinite dimensional space, in the infinite dimensional case. So before we prove it, let me first show you a special case. The special case is that the linearized operator at 0 has a trivial kernel. Okay, so in this case, we can use the infinite dimensional inverse function theorem. So because the linearized operator has a trivial kernel, and the linearized operator, as we have assumed, it is elliptic, then it is actually isomorphism between holder space. This is known to be the famous Schauder theory. Okay. Then because the linearized operator is an isomorphism, we can use the infinite dimensional inverse function theorem. So if you do not familiar with it, you can think of the finite dimensional inverse function theorem. And if the linearized map of a mapping is invertible, then locally it is invertible. That function itself is invertible, and that the mapping itself is invertible. And the proof uses, at least to my knowledge, there is a famous proof using contraction mapping theorem, and the contraction mapping theorem also works in infinite dimensional setting, say in a Banach space. So we can so using this inverse function theorem, there exists a psi, which is the inverse to our Euler Lagrange operator, such that psi composed with mu equals to mu composed with c u equals to u. Of course, this only holds locally in a neighborhood of the 0 section. And in the following, I will just omit this fact. So you should keep in mind that everything we'll do is local. Okay, and moreover, here we can use another elliptic fact, which is the elliptic theory. And we know that C is bounded and Lipschitz as a map from L2 to W22. So it is bounded and Lipschitz from L2 space to the Sobolev space. So here I want to remind you that in all the discussion, we always assume that our manifold is compact. So all these Sobolev norms can be controlled by our Holder norm. And this is actually important. Later we'll see that this is essential to in many cases because we are using some analysis to control the L2 norm of the Euler-Lagrange operator acting on a function. Of course. So let me explain one more, a little bit more words about this fact. And this fact comes from that also the elliptic theory that tells us that if the elliptic operator has a trivial kernel, then it is also a isomorphism between the W22 space and L2 space. So we also have the so-called the regularity theory of the elliptic operators in Sobolev spaces. All right, so once we have this, we have the following computation. So we can use the fundamental theory of calculus. Of course, in the infinite dimensional setting, but we still have such a theory. It says that it is integral from 0 to 1 dt f tu dt. Sorry, I need to say here we don't have, we haven't used any infinite dimensional theory. And this equals to use the derivative of the functional is exactly the Euler-Lagrange operator. So we use the definition of Euler-Lagrange operator. It equals to mtu times u du. Okay, so this is the difference between these two functional, and this functional's value at two different points, and we want to estimate it. So on one hand, we know that because C is bounded and Lipschitz from L2 space to W22 space, we know that U with W22 norm equals to C composed with M, U. Here I use the fact that the C and the U are invertible to each other, are inverse to each other. And this is bounded by, use the Lipschitz property of C, C times the Lagrange operator acting on U. On the other hand, this Euler-Lagrange operator acting on Tu minus it acting on 0, we can use the local expansion. It will tells us that it equals to first T times the linearized part, T times Lu, and plus T times some higher order term of U here. Because when we take derivative of f, we have at the most second order derivative of u. So here we also have at the most the second order derivative of u plus b times first order derivative of u plus c times u. So here a and b are possibly also the sections in the correct bundle. And this implies that MTU, remember that we always assume that 0 is a stationary point of the function. Also, the Euler Lagrange operator acting on 0 gives us 0. So the L2 norm of this M acting on TU equals to the L2 norm on the right-hand side. And right-hand side is some number C times T times U whose W22 norm. Okay, because the right-hand side we have like at most the second order derivative of that U. And this is bounded by C times T from our previous inequality. This inequality, this is bounded by C times T times MU L2 norm. All right, and this tells us we can estimate our previous difference of FU and F0. It is bounded by the integral from 0 to 1, the integral of M TU absolute value times U absolute value. And here we can use Cauchy-Schwarz inequality. Cauchy-Schwarz inequality tells us that this is bounded by the integral from 0 to 1, the L2 norm of MTU times U whose L2 norm dt times and this is bounded by, now we use this inequality. This is bounded by the integral from 0 to 1 C times T times M U L2 norm times for U, its L2 norm is bounded by W22 norm. So we can use this inequality to show that this equals to MU L2 norm dt, and this equals to C times MU L2 norm squared. Okay, so you can see that this gives us the Lojasiewicz inequality with exponent beta equal to 1/2. But in general, we know that if we know that the inequality for 1/2, if U is sufficiently small, then this number is very small, then we can, if we raise its exponent, it only becomes smaller. So this is a special case where we can prove Lojasiewicz inequality. Okay, so after we finish the proof, if we look back, we see that we actually it did not use anything about analyticity of the function. Okay, so even the function now is not analytic, we can still prove it. So the point is that if L has trivial kernel, then we actually the Euler Lagrange operator is actually invertible. In the finite dimensional analogy, it means that the analytic the function f has not a critical. We have the proof. We have the inequality for a function f at a non-critical point. If you still remember from the lecture 1, that at a non-critical point, we always have a Lojasiewicz type inequality. So the interesting situation is that this linearized operator that has non-trivial kernel. In that case, the Euler Lagrange operator is not invertible. Does not have an inverse, namely this critical point. Namely, we can understand it as that the functional the functional has a the functional has a non-trivial critical point at 0, and that's the interesting case for this inequality. Okay, so now our goal is to prove Lojasiewicz inequality in the case that the linearized operator has non-trivial kernel. So it can have non-trivial kernel, and actually, in an element in the non-trivial kernel, we call it K, is called Jacobi field. Okay, and there's one important thing from elliptic theory, which says that if the linearized operator is elliptic, then the dimension of this kernel, or we call the space of Jacobi fields, is finite. It has a finite dimensional kernel. This is very important because if the kernel is infinite dimension, then it would make the problem much more complicated. And the finite dimensional kernel somehow more or less allow us to use some finite dimensional idea to handle with this problem. Okay, so as we explained before, so the Jacobi field or the non-trivial kernel characterize those what we call the degenerate directions. Okay, so here I draw two pictures. The first picture shows an isolated critical point, and the red point is the critical point. So locally, it is the unique critical point, and in this case, we we can think of it as the Hessian of the function is non-degenerate. So locally, we have a nice expression of this expression of this function. And the second picture indicates some possible degenerate directions. So for instance, think of this red set as a critical point, and this is, for instance, one of the critical points. From the finite dimensional Lojasiewicz inequality, we know that these critical points should have the same value of the functions. And the important thing of degeneracy is that it tells near the point there are some direction that the value of the function would not change too much. So these are the hard directions that we to allow us to handle with the difference. Actually, one-dimensional Lojasiewicz inequality tells us that these degenerate directions are actually the most difficult direction to handle with to prove the Lojasiewicz inequality. If locally it is invertible, and we can use, for instance, the mean value theorem, which we have seen in the first lecture, to prove the Lojasiewicz inequality for a very strong exponent. Okay, so in order to prove the Simon's Lojasiewicz inequality, the key idea is to straighten these degenerate directions. Okay, so why is that? If we can straighten these directions, then there are some finite dimension from elliptic theory, that finite dimensional space that we want to use Lojasiewicz inequality. On the orthogonal space to that finite dimensional space, it is an infinite dimensional space, but we can use the similar idea as previously we have used for invertible case, for the case that the L is invertible, to prove a bound on the difference of the value of the functional. Okay, so in other words, we want to decompose the space into two parts. On a finite dimensional part, we want to use Lojasiewicz inequality in finite dimension to get a bound in the form of Lojasiewicz inequality. On the complement of it, although it is infinite dimensions, but we can use somehow more or less the inverse function theory to show that we also have a version of the Lojasiewicz inequality on that part of the space. Okay, and that straighten strategy is called Lyapunov-Schmitz reduction. The key idea of Lyapunov-Schmitz reduction is to construct an inverse even the Hessian of a map is degenerate. Okay, maybe I'll write okay, so suppose F is a map from U to V, where they are both subsets in the Euclidean space. And if df is invertible, then we know from implicit function theory that locally we have an inverse. What if it is not? If it is not, the df is not invertible, namely df is degenerate, we still want to construct an inverse. So Lyapunov-Schmitz introduced this tool to study PDE problems. So this is also a theorem in infinite dimensional space. And let me describe a finite dimensional analogy. So suppose the origin lies inside the set omega, and we have a function capital F is defined in this omega, where 0 is a critical point of it. And the kernel of the Hessian of the critical point is equals to RQ times 0. Here, Q might be some positive number, namely the kernel of the Hessian matrix is non-trivial. Then there exists a map C, which can be viewed as a inverse of the gradient of this map. And in particular, C send the set where for Y lies in some straightened. So this is also a local theorem, but let me state it. It looks like globally. So for any Y lies in the kernel of the Hessian times 0, where the gradient of F composed with CY is 0, namely it is for those Y lies in the kernel space where they are the critical point of F composed with C, it equals to the original critical points. So here I draw a picture to illustrate what's happening. So suppose this is our function F, and the red points are the critical, are the critical points. Because the function looks like this, we know that, for instance, for a critical point here, the Hessian must have a kernel along the direction of these critical points. And then we want to find, then the Lyapunov-Schmitz reduction tells us that we can find the inverse, we can find the mapping more or less to the, can be viewed as an inverse to the gradient of this, to the gradient of this function, and it can straighten these critical sets. So now the critical sets all lies in a one-dimensional linear subspace. Okay, so this is the idea of the Lyapunov-Schmitz reduction. So you can imagine that we want to also have an infinite dimension of it. And in the infinite dimensional case, we want to make those points in the kernel, namely all those Jacobi fields. We want to they are at the linear level. Let me say in the following way. So they are the critical points. They are the kernel of the linearized operator, and for the original Euler Lagrange operator, there possibly be some critical points near the zero section, and we want to find use the Lyapunov-Schmidt reduction to use these Jacobi fields, namely those vectors in the finite dimensional kernel, to represent those critical points. And once we can do that, we can reduce the problem into, as we said before, into a problem on the finite dimensional space and its complement. And on each one of it, we have a nice description. Okay, so let me state the infinite dimensional version of the Lyapunov-Schmidt reduction. So let us recall our setting. So M is the Euler Lagrange operator, L is the linearized operator, and K is the kernel. Then we can define a projection map PK, which is the projection to projection operator to K. Okay, so now we can define another operator, which is called N. So N acting on U equals to, it is defined to be the projection of U to the kernel plus the original Euler Lagrange operator. Actually, this is also what how Lyapunov-Schmidt worked in finite dimensional case. So one can actually construct that inverse map explicitly. Okay, so there are some properties of this new operator N. The first is that N0 is also 0. This is not a surprise because either the projection and Euler Lagrange operator acting on 0 is 0. And second, the linearization of N is exactly the linearization of these two operators, and the projection operator itself is, the projection operator itself, it is linear, so it equals to PK plus the linearization of the Euler Lagrange operator, which is exactly the linearized operator. And now we know that this operator has images in the kernel of the linearized operator, and this operator has only kernel, that finite dimensional kernel. Elsewhere it is non-zero. So this operator has trivial kernel. So now we can repeat our discussion before to conclude that locally, the new operator N from C2 alpha to C0 alpha, again, use the Schauder theory, has an inverse. And we call it C. So this operator is exactly the Lyapunov-Schmidt, the C appeared before in the finite dimensional space. Okay, so let us examine some properties of C. So first of all, C is bounded and Lipschitz from L2 to W22, just like previously in the invertible case. Namely, let me write it down. So we have C F1 minus Psi F2 whose W22 norm is bounded by C times F1 minus F2 whose L2 norm. So you can see that this is actually the same as previously. When the linearized operator is invertible, then the inverse to the Euler-Lagrange operator also satisfies this property. So this Psi really looks like an inverse to the Euler-Lagrange operator. And the second, if phi1, phi2 up to phi k is an orthonormal basis for the finite dimensional kernel space of the linearized operator, then we have the following computation. First, A composed with Psi acting on the summation of some linear combination of these vectors. Because Psi is inverse to n, then this is just itself. On the other hand, notice that n equals to the projection to k add the Euler-Lagrange operator. So what we can conclude is that as a consequence, if we use the perpendicular to denote the projection to the complement of the kernel space, then we would have the Euler-Lagrange operator composed with C acting on a linear combination of those Jacobi fields, namely the points in the kernel space, whose projection to the complement of the kernel is 0. So this tells us that if we compose with the Euler-Lagrange operator with this Psi, the Lyapunov-Schmitz operator, then then it will only maps the kernel space to the kernel space. In other words, it's just like in the finite dimensional analogy. It straightens the points. Those critical points. You still think of that the Jacobi fields, namely the kernel of the linearized operators, are more or less the critical points. Okay, so this is exactly what I called straighten before. Okay, so now let me sketch the proof of Simon-Lojasiewicz inequality. So I'll only sketch the proof. So we'll denote by F to be the restriction of this functional, we restrict it on the kernel space K. And then F is an analytic function on a finite dimensional space. Yeah, it is also only defined on the kernel space, and from the elliptic theory, the kernel space K is finite dimensions. And F is analytic because previously we have assumed that the functional is analytic functional. Okay, then there are 3 steps to prove a Lojasiewicz inequality in the infinite dimensional version. So first, we want to show that Fu minus the value of the projection of U into the kernel space, and we consider the functional value of that projection. This is bounded by C times mu L2 north square. Okay, so let me remind you, this is exactly F acting on the projection of U to the kernel space. All right, so this is very similar to the case where L is invertible. Okay, so the basic idea is that we just if we just minus the component in the kernel space, then we are actually working on the complement of the kernel space, and on that space we have some nice estimate, just like using an inverse function theorem, which we have discussed before. Okay, then the second step, we use classical Lojasiewicz inequality for this function f. So f pku minus f0. So now because f is the restriction on a finite dimensional space, so we can view it as a classical analytic function on a finite dimensional Euclidean space. So there exists a component beta such that the difference between pku and 0, where we evaluate the function f, is bounded by a constant c times the gradient of f, the gradient of f at this point pku. So this is just the finite dimensional Lojasiewicz inequality. Okay. So the last step, so combine this and this, we have already proved like an upper bound of fu minus f0. Again, so aware that this equals to f0. However, this is not mu L2 norm. This is gradient of this function f in a finite dimensional space. So the third step, we want to show that the gradient of f evaluated pku, it is bounded by a constant c times L2 norm of m. Okay, and here we need to use some properties of the Lyapunov-Schmidt operator. Actually, in the first one, we also in the first step we also use the property of C. So in the first step and third step, we want to use C to extract the information of that finite dimensional space, and we distinguish the behavior of the Lagrange operator on the finite dimensional space and the complement, which is an infinite dimensional space. Okay, then we combine in step 1, 2, 3. We have that this difference of fu and f0 is bounded from to certain exponent here, and is bounded from above by a constant times the L2 norm of Euler Lagrange operator acting on U. Okay, so this is a very sketchy. I want to refer you to Leon Simon's work to see how to prove it rigorously with more details. Okay, so finally, let me conclude the second lecture by discuss some applications. So recall that we have this where Lyapunov, the Lojasiewicz inequality proved by Simon. It says that the difference between the value of the functionals at the two different points to the power of beta is bounded by C times the Euler Lagrange operator acting on that function, that point U, in L2 norm. Okay, so in the case where the f is the area functional, a straightforward application says that in an analytic manifold, so locally, the minimal surfaces have the same area. Okay, so if we have a minimal surface, then in a tubular neighborhood or in other or consider the small C2 alpha graph over that minimal surface, if there's another minimal surface, then it must have the same area as this minimal surface. So together with some compactness theorem of minimal surface, for instance, there are some famous the compactness theorem of minimal surfaces in three-dimensional manifold with positive Ricci curvature, proved by Choi and Shen. We know that the minimal surfaces, the area of minimal surfaces in such a manifold must have isolated areas. The value of the area are actually isolated if the manifold is an analytic manifold. Okay, so if F is a differential energy, then in an analytic manifold, Leo-Simon proved that the tangent map of a harmonic map at a singular point must be unique. Okay, so in general, if we take we consider tangent map of harmonic map, it is defined by a subsequentially limit, and use the Lojasiewicz inequality. Leo-Simon proved that the tangent map must be unique. So it is independent of the choice of the subsequence of the blow up scales to infinity. Okay, so these are two applications. I will explain more in the third lecture, and in the third lecture we will see a specific example, which is about the self-shrinkers of mean curvature flow, and we'll discuss about how to derive a Lojasiewicz inequality for a special class of self-shrinkers. Okay, so let me stop for the second.